You're hanging with Huzik. This one's about the autoionization of water, as we call it, and it'll also touch on some ideas of what pH is exactly, what pOH is, the idea of Kw, pKw, and some other relationships with acid-base chemistry. Okay, so let's talk about the autoionization of water. What this concept is in chemistry, and if you've thought about just having pure water before, this will maybe be a bit marvelous for you to find out. So if you just have a container of pure water, distilled water, so it's supposed to be nothing but H2O in there, no salt ions, no chlorides, no calcium ions, nothing like that. Okay, if we look at what's actually happening in that container of water, in reality, it's not just H2O molecules, but those H2O molecules exist in equilibrium with hydroxide and hydronium ions, okay? And this is very much akin to other acid-base equilibria in that most of it actually lies to the left and a little of it lies over here. Okay, so what I'm telling you is that in pure water, you actually do have some ions. There are always some hydroxide and hydronium ions present in any sample of water. And what's also important to note about this reaction is that it's endothermic. And you might have guessed that it's endothermic, meaning the energy term is on the left in the reactants. You might have guessed that because it's basically a decomposition reaction, right? Oh, I haven't balanced it correctly, so there we go. It's basically a decomposition reaction, right, where we have one molecule on the left breaking into parts on the right-hand side. Well, the truth about this, okay, is that at 25 degrees Celsius, the product of the concentration of I should go one step earlier. The concentration of hydroxide is obviously equal to the concentration of hydronium. And as long as it's at 25 degrees Celsius, those concentrations are both 1.0 times 10 to the minus 7 moles per liter. Okay, so the thing about this is that you'll recall that we looked in the last lesson about how we could calculate pH. And we said that the formula for that was that pH is the negative log of the H3O plus or of the H plus concentration. So if you apply that here, right, sub that in for the H3O plus concentration, you'll get the negative log of 1.0 times 10 to the minus 7, and you'll notice that that equals 7. Now, this is very familiar because we said that a pH of 7 is neutral, and of course it is. It's pure water, like we discussed. So we expect the pH to be 7 for pure water. So this kind of hopefully squares the circle for you on why the scale goes from 0 to 14 and why 7 is considered neutral. What I'll tell you is there's another value that works in tandem with pH, and that's called the pOH. And you can probably guess if pH is all about H plus and hydronium ion, the pOH is all about the hydroxide ion. So pOH is the negative log of the hydroxide concentration. So we tend to use this more when we're talking about bases, but we can use it for neutral water. And of course, for neutral water, we're going to end up getting the exact same value of 7 that we got for pH. Okay, so the pOH is also 7 for pure water. Well, the relationship that comes out of this, and it's true all the time, is that the pH plus the pOH, pH plus pOH, is equal to 14. Okay, and this is for water at 25 degrees Celsius. Okay, if we change the temperature, pause the video for a second and ask yourself, how do you imagine all these numbers to change if we, what are we going to do first? If we decrease the temperature. If we decrease the temperature, how do you expect these numbers to change? All right, well, let's check it out. So, according to Le Chatelier's principle, if we decrease the temperature, it means we're lowering the energy here. It means we're decreasing something on the left-hand side of the equilibrium. What's going to happen if we do that is it's going to shift to the left to try and replace the heat that we took away, in a way, okay? I like to think of applying Le Chatelier's principle, like applying the energy like it's a reactant or product. So we're applying the idea of energy being a reactant. If the temperature is going down, we got to put more, the equilibrium is going to shift to try and put more energy in, okay? What's that going to do? It's going to draw down how much hydroxide and hydronium ion there are, and it's going to draw them down equally, right? So bear with me here because I'm going to keep on writing in red, but if we cooled, I say bear with me because, like, we don't usually write in red when we're cooling something, but if we cooled the system, okay, what we would see is a shift left, right? Correct? A shift left, okay? And then we would see a decrease in this, and we would see a decrease in that, right? Okay, so what were they at 25 degrees? They were 10 to the minus 7, okay? So what's it look like if we decrease them? Let's say, for example, now maybe the hydroxide goes down to 1.0 times 10 to the minus 8, right? And same with the hydronium because they're going to be the same. So what does that mean? Well, if they both go down to 10 to the minus 8, well, now the pH of the system is the negative log of 1.0 times 10 to the minus 8, which means the pH of the system is 8. And what I'm going to tell you is that this is still neutral, okay? Still neutral. So we had neutrality here when pH was 7, but we can also have neutrality here when pH is 8. So this is the crazy thing about using the term neutral. The term neutral isn't tied to the idea of the pH being 7. What it's tied to is that the concept that the pH and the pOH are both the same, right? The concentration of hydronium and the concentration of hydroxide are the same, so it's neutral. They aren't necessarily both 7 all the time. They're only both 7 at 25 degrees Celsius. And so this pH and pOH equaling 14 is specific to being at 25 degrees. If we cool the system down, like we did here in this example, now pH and pOH could be, up to something like 16, right? That's just the way it goes. If we go the other way around, if we heat the system, it's going to shift to the right. We're going to get increased concentrations of hydronium and hydroxide in tandem, and now all of a sudden we could have neutrality at like pH 6 and pOH 6. That's the name of the game. Okay, a little bit more on this ever-important relationship, this ever-important equilibrium of the water equilibrium. Remember that we said the hydronium ion is always going to be equal in concentration to the hydroxide ion. Well, if we make an equilibrium constant, because this is a solution in equilibrium, then we would do that in the same way that we would make any other Kc or K equilibrium. And for water, we call it Kw. And Kw is going to be the concentrations of the products. So there they are, multiplied together, divided by the concentration of the reactants. But hold on a second. The reactant is liquid water, and we said we don't include that concentration in any of these calculations. So that is a fact. We don't include it. So actually Kw is a constant. It's called the ion product constant for water, and that's the equation for it. So this is called the ion product constant for water. And because we said at 25 degrees, very important that you realize this is a temperature dependent value, but at 25 degrees, we said that each one of these guys is equal to 1.0 times 10 to the minus 7. So what does it equal if you multiply them together? Well, if you multiply them together, then that's going to give us, let's just get my pen back sorted here. That's going to give us 1.0 times 10 to the minus 14. Okay, so the full relationship of Kw that you could write is that at 25 degrees Celsius, we see that Kw, which is the product of the two water ions, is equal to 1.0 times 10 to the minus 14. That means in any solution, if you knew, for example, I don't know, maybe in one of our previous examples, I think we calculated a hydroxide ion concentration of like 0.0024 molar. You could ask yourself, what's the hydronium ion concentration at 25 degrees Celsius? Okay, and it does need to be specified that it's at 25 degrees Celsius, otherwise there could be a little bit of ambiguity. In most of these questions in high school chemistry, they'll just assume it's at 25 degrees. If it wasn't, you would need a big chart of a little bit more details on how it changes. I would expect you to generally need to know qualitatively how it changes with temperature, like we did on the previous slide. If temperature goes up, you're going to have values greater than 10 to the minus 7. And if the temperature goes down, you're going to have values that are lower than 10 to the minus 7. Okay, so how we would then do this is we would say, all right, Kw, which we know is equal to 1.0 times 10 to the minus 14. Why do we know that? Because it's at 25 degrees Celsius. We know that is going to be the product of the two ions. And we know that one of those ions, the hydroxide ion, has that concentration. So then we can just kind of like solve for X, solve for H3O+, and it's going to be the other concentration. Okay, I did that. It looks like it turns out to be 4.2 times 10 to the minus 12. Okay. Now, that's moles per liter, by the way. Now, you could ask yourself, does this seem to be correct? Well, remember that they have to multiply to be 10 to the minus 14. So this one here, I'm going to try and just kind of highlight this. This one here, the hydroxide ion, it's relatively high, right? This is a basic solution, or an alkaline solution. So we would expect this one, the complementary hydronium ion concentration, to be really low, and in fact it is. So it looks right, okay? So what we could also ask, why not, is the knock-on question: what's the pH of the solution? What's the pH of the solution? Well, then we would take the negative log of 4.2 times 10 to the minus 12. Punch that into your calculator. You do that, you get, it's about 11.4. Okay, so then you can ask yourself, a pH of 11.4 for this solution. Does that make sense? Well, yes, because that suggests it's an alkaline solution, right? Which we know it is because it started with a relatively high hydroxide concentration. So let's just do a quick recap to see what we've established here so far. So we know that because of the autoionization of water, pH is equal to the negative log of the hydronium ion concentration. pOH is equal to the negative log of the hydroxide concentration. We know that pH plus pOH is going to be equal to 14 at 25 degrees. If we cool it, that number is going to go up. If we warm it, that number is going to go down. We know that the ion product constant for water, Kw, is equal to the hydroxide concentration times the hydronium concentration, and we know that that product is equal to 1.0 times 10 to the minus 14 at 25 degrees. Okay, so we're starting to establish some really universal relationships that they apply all the time to all aqueous solutions. And so you can see why Arrhenius was originally obsessed with the concentration, that really acid-base chemistry is all about hydronium and hydroxide. Acids produce hydroxide in solution, bases produce, oh sorry, I flipped that backwards. Acids produce hydronium in solution, and bases produce hydroxide. What I'm telling you now is that those actually exist all the time, right? It's just that if one goes up, the other one goes down, okay? So if we see if pH goes up, then the pOH goes down, okay? So it's just an up and down relationship communicating how acidic or how alkaline basic is a solution. We're going to throw in a couple more relationships here. Last really important relationship that I want to introduce to you in this video is going back to Bronsted-Lowry conjugate acid-base pairs. And I'll show how this all links up in a minute. But let's examine this this equilibrium on the board here. We looked at it before. This is ammonium. Ammonium is a weak base, okay? I don't have to write weak because you can see it's weak from that equilibrium symbol, but it's a base. What's its conjugate acid? Remember, its conjugate acid is just the protonated form, so that's the conjugate acid over there. It's the hydronium ion. Okay, no it's not. It's the ammonium ion. There we are. Okay, so then what's acting as an acid here? Water's actually acting as an acid. And what's the conjugate base for water? The conjugate base for water is the OH minus, the hydroxide. Okay? So we said that we could make a Kb expression here, right? Remember that? So remember for the Kb of NH3, we said it would be the products, just like any equilibrium constant, the products over the reactants. So here's the products, there's the reactants, but we leave water out because we don't take the concentration of water in water. I've told you that a whole bunch, okay? So that's the Kb expression for ammonia, all right? Now, what's interesting is that the conjugate acid of a weak base does function as an acid. I'm going to write that out. The conjugate acid of a weak base is a functional acid. Functional acid. What do I mean by that? I mean, like, if for some reason we could just put NH4 plus into solution with water, and let's pause here and imagine, like, you know, practically how might this happen? Well, maybe we have like an ammonium salt. So an example of that would be, I'm just gonna make a little salt shaker, even though it's not table salt. Why not? We might have an ammonium salt like NH4Cl, okay, ammonium chloride. Well, I'm telling you, we can forget about the chloride, and more on why we can do that later. But if we were putting this salt into some solution, okay, what we would find out is that solution would end up having a pH, you know, an acidic pH, okay? I should, now that you know what you know about pH, I can't just say less than 7 and assume we know it's acidic. I'm just going to go ahead and write the word in red. It's acidic, okay? Okay, so this would be an acidic solution. Trust me. So why is that? Well, what does an acid do according to Bronsted-Lowry? It donates its proton, right? So it's going to donate a proton here. It's going to create the conjugate base NH3, and it's going to create some hydronium ion, right? As it protonates water, okay? So if you have on its own NH4 plus in solution, it functions as an acid. Let's make the Ka for NH4 plus as an acid. What's that look like? Well, follow the rules. Got NH3 concentration, you got H3O plus concentration, and it's all divided by the original acid. We don't include water, of course, okay? What happens then if we take the Ka for an acid and we multiply it by the Kb for its conjugate base. Conjugate base. What happens if we multiply those two together? Well, let's just plug in the algebra here and see. So you get NH3, you get H3O plus on the top, you got NH4 plus on the bottom, and you're going to multiply that by, don't you just love my color coding? We're going to multiply that by NH4 plus and hydroxide ion. And do you see where this is going? Do you see what happens here? That cancels, that cancels, that cancels, that cancels. Holy moly, what do we have? We have that Ka for an acid times the Kb of its conjugate base is always equal to Kw, right? Which is the concentration of H3O plus times the concentration of OH minus, which is equal to 1.0 times 10 to the minus 14, as long as we haven't deviated from 25 degrees, okay? So this is a super important relationship for Bronsted-Lowry acids and bases. And again, the most important thing I would emphasize is that it's the Ka for an acid, and it's the Kb for the conjugate base of that acid, okay? So let's do one example. Earlier we said, so I might say, what is the Ka for the ammonium ion, all right? And we looked up on a, we could look up on a paper, and you know, we can work with this a little bit more in subsequent lessons, but we can look up that the Kb of NH3 is 1.8 times 10 to the minus 5. I think that's what it was. All right. So what do we do then? We can plug in. Well, we know that the Ka then is going to be equal to Kw divided by that Kb. It's going to be equal to 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. So do the math on that. So 1 divided by 1.8 is 0.56. Okay, so I can do it this way, 0.56. And then if we do the exponent math here, it's negative 14 minus 5. So negative 14 plus 5, so 10 to the minus 9. And then if we make this number bigger, we're going to make this number smaller. So there we go. So the Ka then of the ammonium ion is equal to 5.6 times 10 to the minus 10. And we figured that out by using the Ka times Kb acid conjugate base relationship. Thanks for hanging in there. I hope this video helps establish some solid foundation to solve a bunch of chemistry problems in acid base later on.